So we've discussed lethal dose 50 and effective dose 50, and those are all talking about toxicity in terms of a single dose. However, actual toxicity depends on various factors. Not only the exposure dose, but the length of time during which an individual is exposed to that toxin. Individual sensitivity varies greatly. I sometimes give the example of my mom and I were in the kitchen one day, and there was she suddenly experienced respiratory issues. She had trouble breathing, and so I took her to the ER, and we found an ER full of people in the waiting room that were having breathing difficulties. And it turned out that they had done a mosquito spraying. And even though I was in the same room with her when the plane passed by, I was not sensitive to that chemical, and I didn't experience any trouble. So individual sensitivity is a factor. Solubility in water or fat, which is the term for bioaccumulation. First of all, if it's soluble in water, then it can accumulate in fat, and that leads to bioaccumulation, which we've talked about before, and I have on a future slide to review it. Same with biomagnification, the moving up the food chain. The age of the individual makes a difference. As people get older, their immune systems diminish a bit, and so they are therefore more sensitive to a toxin and to a bacteria or infectious agent as well. And young children have high metabolisms, so the toxicity may have a different effect on them. Persistence, which is how long the chemical lasts in the atmosphere, makes a big difference. So we look at the half-life of various chemicals, and the longer the half-life of the chemical, the more it goes back up to this, the more exposures, the longer the length of not only individual time, but repeated exposure if it's persistent in the environment. So that affects the toxicity. And last, there can be a synergistic interaction, which is when two risks together cause more harm than either one alone. And I think the best known example of that is smoking, cigarette smoking, and asbestos exposure. So let's say the risk of cigarette smoking gives you a risk of 1 to come down with cancer, and let's say the exposure to asbestos gives you a risk factor of 1 for coming down with cancer. Then those two things together, someone smokes tobacco and let's say works building ships and is exposed to asbestos a lot, then their chance or their risk of getting cancer is not 1 plus 1. It's not 1 and it's not 1 plus 1. It's a number greater than 1 plus 1. And that's a synergistic interaction. And that becomes important when you look at the sheer number of chemicals that have been developed synthetically since the 1950s. And even if we test one of those chemicals or two of those chemicals individually, we don't know for a fact whether if we combine those two chemicals together, would there be a synergistic interaction that causes more harm than either one of those alone. Okay, now to revisit the terms bioaccumulation and biomagnification and persistence. So bioaccumulation is within an individual organism, and it's when there's an increase in concentration of a chemical within the organism over time because it's first of all soluble in water, so it can get into the organism, and it accumulates in the fat of that individual organism. Biomagnification is how there's an increase in chemical concentration in animal tissues as you move up a food chain. So the famous example is DDT in water, which is only 0.00005 parts per million, so very little DDT in the water. But there's a huge jump even when you move up to the level of plankton, these microscopic, typically microscopic unicellular organisms. And then it's up to 0.26 parts per million when you get to a small fish, and then 1.28 parts per million when you get to a larger fish, and then all the way up to 13.8 parts per million when it reached ospreys and started. So it's bioaccumulating within the osprey, but it also biomagnifies as you move up the food chain. So another issue is persistence. How long does the chemical stay in the environment? So let's look at the next slide. This shows the persistence of various common chemicals that might have been found in the atmosphere. So the first one is malathion insecticide. It's really a pretty dangerous insecticide. It was very popular in Florida, but even though it's a very damaging insecticide, it has a half-life of 1 day, which is relatively short. And as you move up the line here to Roundup, which you may have heard of before, that has a half-life of 7 to 70 days in water. So that's longer, but not horrible yet. As you move up to chemicals such as DDT, they have a half-life of 30 years in soil. So let's review what that term half-life means. If you had a beginning concentration of DDT of 100 units of DDT, hypothetical units, after 30 years, the DDT is not gone. You started with 100 units, and then after 30 years, you still have 50 units of DDT. And if you wait another 30 years, which is 60 years out from the initial dose of DDT, you still have 25 units. So you started with 100 units. After 60 years, you have 25 units of DDT remaining. And another famous example is Agent Orange, which also has a half-life similar to that of DDT, and it's still present in the soil in Vietnam. And a couple of years ago, the U.S. military actually began cleaning up the soil there. Okay, next we're going to look at epidemiological studies. So epidemiological can be with chemicals or it can be biological. So epidemiology is a field of science that seeks to study causes and patterns of diseases in animals and human populations. So they're looking at large groups of individuals, and it even could be global, or it could be within a state, or it could be within a country. And again, it could be about a chemical that's causing a disease, or it could be about a biological factor, a pathogen causing a disease. So studies fall into two main categories: a retrospective study, which is one which monitors populations that were exposed to a chemical at some point in the time in the past and looks for possible effects. So let's say we just found out that DDT, well, let's take the population in Norelco that was exposed to air pollutants from a chemical factory and an oil refinery. So once it was determined that these populations were exposed, we can go back and look at what happened to them. What are their rates? And so that's one type of study. Another type of study is prospective studies, where you monitor populations that might become exposed to chemicals sometime in the future. So you plan it, you look ahead. And the best types of studies are prospective, randomized, double-blind studies. And that's the type of study you would have for medications such as vaccines. So prospective means it's planned out. Randomized means the test subjects are randomized in terms of gender, race, age, and all kinds of factors, maybe pre-existing conditions. They would all have an equal number in both groups. Double-blind means that the test subjects, or the research participants, you might say, are not aware of whether they're being given the medication or a placebo. The double-blind part comes in with the people who are administering the medication in the study. So the doctors and nurses and those who are monitoring the study also don't know whether the patient or the research participant is receiving the placebo or the medication. And that gives us the most reliable type of information. The other factor here is the number of research participants. The larger the number of research participants, the stronger the study. And the more that we can remove any other factors that might be affecting the study, the better. Okay, now again, talking both biological and chemical routes of exposure here. On the left, we have infectious diseases, and on the right, we have chemical. If you look on the left at infectious diseases and on the right, chemical routes of exposures for chemical routes of exposure, and compare them, you can see that there are some things in common. For example, there's air can spread infectious diseases, and air can spread chemicals that expose us to risk of illness. You can have food spread a disease such as salmonella, and you can also have something in food, maybe the chemicals that make up a water bottle, for example, might transmit a chemical to a person. Same with maybe hormones in milk. You can see that water is common to both, and you can see that for infectious disease, you can have a spread from animals, but not a chemical spread. You can have domesticated animals and like livestock and pets spreading disease, but not so for chemicals. You can have infectious diseases spread among other individuals, other humans. And then on this chart on the right, they point out that chemical exposures in the mom can pass to the fetuses and babies. They don't point that out in the side of infectious diseases, but in fact, that is what happens. I'm going to pause the screencast here, and then in the next section, we will look at risk analysis.